Video retargeting aims to change the aspect ratio of a video by removing non-salient content beyond what can be achieved by traditional cropping or uniform scaling. We propose a novel video retargeting algorithm that carves around dynamic salient content while shrinking and minimizing the distortion of the non-salient content. Our approach is capable of handling a wide range of challenges, as demonstrated here for a subclip of the 75-second video Apologize by OneRepublic downloaded from YouTube. Our approach does not use geometric constraints in time. Instead, we compute temporally discontinuous seams that avoid sudden salient content artifacts like those caused by occlusions or abrupt motions. Our technique is based on the observation that a static seam applied to each frame in a dynamic scene leads to the optimal temporally coherent result but does not offer enough freedom for video retargeting. Instead, our algorithm measures the difference in appearance by applying the previous seam to the current frame and computing a new seam that minimizes the difference in appearance. Specifically, assume the red seam is the previous seam from the previous frame and we are about to compute the current green seam. In this example row, we compute the cost for removing pixel B if the previous seam removed pixel F. The temporal coherence is the sum of the squared difference between these rows after removal of B and F. We generalize our temporal coherence approach to the spatial domain and propose piecewise seams. Offering more freedom, they are able to carve around important details. To achieve piecewise seams, we measure the change in color gradient when removing a pixel, here exemplarily shown for removing H with respect to A. The vertical gradient before removal is indicated by the blue and orange arrows. As after removal the result has fewer operands as shown on the right, we consider a left and right version of the vertical gradient. We define the change in color gradient as the absolute difference of the vertical gradient before and after removal, summing the contribution of the left and right version. We compare our approach to Rubinstein's forward energy. Notice how our gradient-based measure preserves straight lines more faithfully. In this example, we demonstrate the effectiveness of our spatial coherence measure. Without spatial coherence, the planes are clearly distorted. Comparisons to other authors. We show a still frame for better comparison. Another example of our discontinuous seam carving algorithm computed using gradient-based saliency. In this example, we use our own implementation of Wolf et al.'s optimization approach. Retargeting of a highly dynamic scene. Here, our comparison to Krahenbühl's 2009 approach. The sign on the truck spelling yellow is still readable in our result. A failure case due to many explosions and complex motion patterns. Simple frame-based saliency might lead to inconsistent results, for example in case of abrupt scene changes. We achieve consistency by averaging per frame saliency over spatial temporal regions. In this example, we compare different saliencies with our spatial temporal saliency. Gradient-based saliency distorts the wall in the background, while frame-based saliency causes temporal artifacts. In some cases, higher knowledge about the scene is necessary than saliency can provide. Here, removing the white pillar introduces significant artifacts. To overcome this problem, we designed an interface that allows the user to select important spatial-temporal regions by simply brushing over them. In this case, an external video segmentation algorithm supplies these regions. The user selection can be used as definition of saliency by our algorithm. Note that in contrast to optimization approaches, our algorithm allows retargeting to any desired target size in real time. Our previous example retargeted by user input. More examples obtained by user-selected regions. Comparison to Rubinstein and Alias approach. User-selected regions at the bottom and our resized version. A closing example. Here, the original sequence. Our retargeted result at the bottom, using gradient-based saliency only.